In this episode, we are going to take 4 ideas that often get bundled together in beginner cybersecurity learning and make them feel much more understandable by connecting them to one simple question. How do we protect information and prove trust in a world where data is constantly moving? Symmetric cryptography, asymmetric cryptography, hashing, and quantum-resistant cryptography are all part of that answer, but they do not solve the same problem in the same way. New learners often hear these words and assume they are just different styles of scrambling information, when the real picture is much more interesting and much more useful. Some methods are best for keeping data private. Some are best for helping people exchange trust safely. Some are best for checking whether information has changed. And some are being developed and adopted because the future of computing may weaken older assumptions. Once these ideas are mapped clearly, they stop sounding like separate puzzles and start feeling like related tools for confidentiality, integrity, authentication, and long-term resilience. Before we continue, a quick note. This audio course is part of our companion study series. The first book is a detailed study guide that explains the exam and helps you prepare for it with confidence. The second is a Kindle-only ebook with 1,000 flashcards you can use on your mobile device or Kindle for quick review. You can find both at Cyber.Me in the Bare Metal Study Guide series. A good place to begin is with the word cryptography itself, because many misunderstandings start there. Cryptography is the use of mathematical methods to protect information and support trusted digital communication. It helps make sure that data is not easily understood by the wrong party, that information has not been altered without detection, and that systems or people can trust certain digital actions more confidently. It is not magic, and it is not just a secret language for computers. It is a structured way of using mathematics so that information remains useful to the right people while becoming far less useful to the wrong people. That broad purpose matters because beginners sometimes focus too quickly on specific algorithms and miss the larger pattern. The larger pattern is that different cryptographic methods exist because digital trust has several different needs. Keeping a message secret is not the same thing as proving who sent it, and proving that a file was not altered is not the same thing as encrypting it. Each method belongs to a different part of the trust problem. Symmetric cryptography is the easiest place to start because it is built around one central idea that feels very direct. The same secret key is used to lock the information and unlock it again. If two parties both know that secret key, they can use it to encrypt and decrypt data. This makes symmetric cryptography very good for protecting the confidentiality of information when the key can be shared and managed safely. It is often fast and efficient, which is one reason it remains extremely important in real systems. A beginner can picture it like a locked box where both the sender and the receiver use the same physical key. The strength of the method comes from keeping that shared key secret. If the correct people have it, the message stays private from others. If the wrong person gets it, the protection weakens immediately. That simple dependence on one shared secret is both the great strength and the great challenge of symmetric cryptography. The main advantage of symmetric cryptography is speed. It is generally well suited for protecting large amounts of data, ongoing communication sessions, stored files, backups, and other situations where efficiency matters. Once the secret key relationship is established, the method can protect information without needing the heavier trust exchange logic that some other approaches rely on. The problem appears when you ask how that shared key is supposed to be exchanged safely in the first place. If two people or systems have never communicated before, sending the key insecurely would defeat the whole purpose because anyone who intercepts the key could then read the encrypted data as well. This is one of the biggest reasons beginners should not think of symmetric cryptography as a complete answer by itself. It is excellent at one part of the problem, which is efficient privacy after the key is known, but it does not solve the key exchange problem elegantly on its own. That limitation is what helps explain why asymmetric methods became so important. Asymmetric cryptography approaches the problem differently by using two related keys instead of one shared secret. One key is public, meaning it can be shared openly, while the other is private, meaning it must be protected carefully by its owner. The two keys are mathematically connected, but knowing the public key does not make it practical to derive the private key if the system is designed properly. This changes the trust model in a very important way. A person or system can publish a public key so that others may use it for certain secure actions, while still keeping the private key hidden. This is why asymmetric cryptography is often associated with public key ideas, identity trust, and digital signatures. The beauty of the model is that it reduces the need to exchange a single shared secret before any secure interaction can begin. It does not remove all trust problems, but it handles them in a different and often more flexible way than symmetric cryptography. A helpful way to understand asymmetric cryptography is to picture a special mailbox with two different functions. Anyone can use the public part to drop in a message securely, but only the owner with the private part can open the box and read what was placed inside. That makes the public key useful for protecting confidentiality in some cases, because people can encrypt information in a way that only the holder of the private key can decrypt. The model also supports digital signatures, which reverse the trust direction in an important way. If a person uses the private key to create a signature, others can use the public key to check whether that signature matches and whether the signed content appears unchanged. This gives asymmetric cryptography a powerful dual role. It can help protect confidentiality, and it can help support authenticity and integrity by tying digital actions back to a key owner in a verifiable way. That is why it matters so much in trusted communication. Even though asymmetric cryptography is powerful, it is not simply better than symmetric cryptography in every way. A common beginner mistake is to assume that because asymmetric methods feel more advanced, they should replace symmetric methods entirely. In practice, the two approaches often work together because they solve different parts of the problem well. Symmetric cryptography is usually faster and more practical for protecting large volumes of data. Asymmetric cryptography is especially useful for safer key exchange, identity-related trust, and digital signature functions. Many secure systems use asymmetric methods to establish trust or exchange key material, then switch to symmetric encryption for the actual bulk data protection, because that combination balances efficiency and flexibility. This is a very important lesson because real security design often depends on combining tools rather than choosing one universal winner. The question is not which method sounds more impressive. The question is what role each method plays in building secure communication and trusted digital action. Hashing belongs in this conversation, but it is fundamentally different from both symmetric and asymmetric cryptography. A hash function takes input data and produces a fixed-size output often called a digest or hash value. The important part is that hashing is generally designed as a one-way process. You can take the original data and calculate the hash, but you are not supposed to take the hash and recover the original data directly from it. This means hashing is not mainly about hiding information in a reversible way. It is mainly about creating a compact mathematical fingerprint of the original input. If the input changes, even in a small way, the resulting hash should change as well. That makes hashing extremely useful for integrity checking. A beginner should understand that if encryption is like locking information so it can later be unlocked, hashing is more like stamping information with a signature-like fingerprint that changes when the content changes. It serves a different purpose in digital trust. This different purpose is what makes hashing so important in practice. If a system stores a hash of a file, a message, or a password-related value, it can later compare a new hash calculation to the original and see whether the content appears to be the same. That is useful for detecting accidental corruption, suspicious changes, and other integrity problems. Password handling is one area where beginners often first hear about hashes, because well-designed systems do not need to store plain passwords in readable form. Instead, they can store a protected hash-related representation and later compare results when a user attempts to authenticate. The key lesson is that hashing is not about keeping data secret in the way encryption does. It is about helping systems recognize consistency, detect changes, and avoid storing certain secrets in their raw original form. Once that difference becomes clear, learners stop mixing hashing into the same category as reversible encryption and begin to see why it deserves its own place in security thinking. A common source of confusion is the idea that hashing can be used like encryption if someone simply tries hard enough. That is not the right mental model. Encryption is meant to be reversed by an authorized party who has the proper key. Hashing is meant to be one way, which means its value lies in comparison, not recovery. Another misconception is that if two pieces of data produce the same hash, that always proves they are identical in every possible sense. In practice, strong hash functions are designed to make accidental matches extremely unlikely, but the real security value comes from using well-designed hashing methods appropriately and understanding their limits. A further misconception is that hashing alone proves identity. It can support integrity and certain trust mechanisms, but it does not by itself replace authentication, key management, or digital signature processes. The broader lesson is that hashing is a support tool for integrity and verification, not a universal substitute for encryption or identity control. Once symmetric cryptography, asymmetric cryptography, and hashing are viewed together, the larger picture becomes much clearer. Symmetric methods are strong for efficient confidentiality when a shared secret can be managed. Asymmetric methods help with key exchange, trust establishment, and digital signatures through public and private key relationships. Hashing helps verify integrity and supports secure handling of certain kinds of values without functioning as reversible encryption. These are not competing answers to one question. They are complementary answers to several related questions. A secure connection on the internet, a trusted software update, a verified digital certificate, a protected stored file, and a safe password handling system may all involve some combination of these methods working together. This is why cryptography makes more sense when you think in terms of roles rather than in terms of memorizing definitions. The question to ask is not simply what this method is. The better question is what trust problem this method is helping solve. Quantum-resistant cryptography enters the discussion because the long-term strength of some widely used asymmetric systems depends on mathematical problems that are believed to be hard for ordinary classical computers to solve. That belief has supported modern digital trust for years, but the development of more advanced quantum computing creates concern that some of those problems may become much easier to solve under future conditions. If that happens at meaningful scale, older asymmetric methods that support key exchange and digital signatures could become much weaker than organizations expect. Quantum-resistant cryptography is the effort to design and adopt cryptographic methods that are believed to remain strong even if powerful quantum computers become practical against older approaches. The reason this matters is not that the whole world of cryptography suddenly disappears. The reason it matters is that digital trust depends heavily on asymmetric methods, and those methods support many of the systems people use every day without even noticing them. A beginner should notice something important here. The quantum concern is not aimed equally at every cryptographic method in the same way. Symmetric cryptography and hashing may still require adjustments such as stronger sizes or careful parameter choices, but the most dramatic long-term concern is often around certain older asymmetric systems that depend on mathematical assumptions quantum computing could challenge more directly. That is why quantum-resistant cryptography is such a significant topic even though it may sound futuristic. It is really about preserving the parts of digital trust that help systems establish secure sessions, verify identity, and support trustworthy signatures. If those foundations weaken, then many higher-level services built on top of them also feel the impact. The shift therefore matters because organizations cannot wait until the last second if they want long-lived data, long-term trust relationships, and critical systems to remain secure across technological change. Preparation matters before the threat becomes fully mature. One useful way to think about quantum-resistant cryptography is as a transition effort rather than a single replacement button. Organizations are not simply throwing away the whole field of cryptography and starting over. They are evaluating which older methods may need to be replaced over time, which systems depend on them, how new standards can be adopted safely, and how long protected information must remain secure. This last point matters a great deal because some information is valuable only for a short period, while other information or trust records may need to remain protected or verifiable for years. If an attacker can capture encrypted material now and wait until future capabilities improve, then some data could still be at risk even before a large-scale quantum future arrives. This is why quantum-resistant thinking is about long-term resilience, not panic. It asks how current trust decisions will hold up over time and whether cryptographic choices made today will still make sense in the face of changing computational power. A final beginner misconception worth clearing away is the idea that quantum-resistant cryptography means all existing systems are already broken or that classical cryptography no longer works. That is not the right conclusion. Current cryptographic systems remain deeply important and widely relied upon, and organizations are not expected to abandon sound present-day protections simply because future threats are being studied seriously. The real lesson is that cryptography is not static. It evolves because attackers, computers, mathematics, and trust needs evolve. Good security, therefore, includes not only using strong methods today, but also preparing for how those methods may need to change tomorrow. Symmetric cryptography, asymmetric cryptography, hashing, and quantum-resistant cryptography all fit into that bigger story. They show that digital trust is built from several related ideas, each solving a different problem, each depending on good design and good key management, and each needing to be understood in the context of both current needs and future resilience. By the end of this discussion, the core picture should feel much simpler and more connected. Symmetric cryptography uses one shared secret key and is excellent for efficient confidentiality once that secret can be managed safely. Asymmetric cryptography uses public and private key pairs to help with key exchange, digital signatures, and broader trust relationships. Hashing creates one-way fingerprints that help detect change and support integrity-focused tasks rather than reversible secrecy. Quantum-resistant cryptography looks ahead and seeks methods that will remain trustworthy even if future quantum computing weakens older asymmetric assumptions. These ideas matter because security is not built from one universal cryptographic trick. It is built from different methods solving different trust problems while working together in real systems. Once you understand what each method is really for, cryptography stops feeling like a wall of complex jargon and starts feeling like a practical language for protecting confidentiality, supporting integrity, proving authenticity, and preparing for the future of digital trust.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.